Welcome to everybody. Today we are dealing with a new exercise related to an open section, open thin wallet section. Today we're dealing about with the zeta section. How can you see from this picture? For this zeta section we have a nominal length for the web, that is the 320 millimeters, and the nominal length of the flange, that is 160 millimeters. But for our calculation we must refer to the mean line, that is this line here depicted with the red plane. So we must refer to the length A for the length of our web. A is equal to 300 millimeters, and for both flange, upper and lower flange, we must refer with this length, that is B. B is equal to 150 millimeters. So the thickness of the upper and lower flange and in the thickness of the web are equal both to a thickness that is equal to 20 millimeters. With an SY, so in shear load applied along Y direction, today I have placed the axis in flipped direction with respect to previous video. So now the Y follows the direction from the up to the bottom. So Y positive is in this direction, following the magenta arrow, or following the blue arrow. So X point today in this exercise from the left to the right, and is positive following this direction, always indicated or from the blue line here or from the magenta line here, from these two arrows if you want. So an XCG of this section clearly is equal to B. If I take this reference axis, this is drawing with the blue plane, XCG is equal to B, that is equal to 150 millimeter, and YCG is equal to A over 2. Now we're going to see this calculation in MathCAD. As a disclaimer, an initial disclaimer, Sx is equal to 0 kilonewton, and the formula that we must use to calculate the shear flows is this. You in this formula don't see the contribution clearly of the Sx, that is equal to 0, but now we must to calculate also other two quantity that are the product of inertia Ixy, because this section is not symmetrical. With respect to the x-axis, is not symmetrical with the y-axis. So Ixy is not equal to 0, and today we must calculate this quantity. And furthermore, also the Iyy is not equal to 0. So we have all these quantity here. Clearly we here you don't see the minus sign, because the general relation is Sx times Xx minus Sy Ixy. Here there is a minus sign, divides the denominator, that is this quantity. But if Sx is equal to 0, this quantity is path to 0, and minus times minus is equal plus. So we have plus Sy times Ixy divided by the denominator. So the integral are the same. The integral from 0 to our chosen abscissa of t times x coordinate and t times y coordinate for this other part of the formula. Now this is all the disclaimer for this exercise. This is clearly all the geometrical reference of our section. You can see also here S1, S2 and S3 are the chosen abscissa for the shear flow. So the shear flow, as I said in previous video of the chi section, if you lost this video you can go in playlist and you can see this video. In that video I said that the S1, S2, S3 and Sn represent our chosen abscissa that indicate the positive direction of the shear flow. So the shear flow is positive in the upper flange if moves on from point 1 to point 2. Is positive in the web, the shear flow if move from point 2 to point 3, and the shear flow is positive in the lower flange if moves from point 3 to point 4. So these three axes represent our positive direction of the shear flow. Now we can switch on MATCAD. So now we are on the MATCAD. On the left side of your screen now there is the Z section. On the right side of your screen there is the sheet of MATCAD sheet. We see on the first line all the geometrical data of our section, and A1 is equal to B times T, that is B, the length of the upper flange in this case, and the T is the thickness, so this is the area in millimeter at square power. A2 is equal to A times T, and A3, the third area, this is this third area, the area of the lower flange is equal to the A1, that is because the lower flange is equal to clearly the upper flange. So xg1 is the location with respect to the blue reference axis of the centroid of the first rectangular shape, and is equal to b divided by 2. If you can prove yourself this is the right value. xg2 is equal to b, that is this distance, g2, the coordinate x of the centroid is g2 is equal to 150 millimeter, that is equal to b, and xg3 is equal to 3 divided by 2 times b, because if you make some calculus you can note that this distance is b from point 1 to point 2, but g3 have this other distance that is the clearly b over 2. So b plus b over 2 is equal 3 divided by 2 times b, that is equal, if you want to see, millimeters, is equal to 225 millimeters. So now as always we must to calculate the location of CG, that is equal to the sum of the related area with the related xj1, in this case on the numerator. If you remember, the quantity is the first moment of the area, that in Italian is the momento statico. So the sum of the all of the first moment of area of the all the elementary shape that we divide this z section, divided by the sum of the all the area a1, a2, and 3, the 3, and a3 is equal the xcg. But in this case a1 is equal to a3, and I write this simplified formula, and in the denominator I multiply by 2 the area a1, because a1 plus a3 is the same thing, so 2 times a1 plus a2. I simplified literally the formula, and you can see that xcg and ycg, the same discussion for the y coordinate for yg1, yg2 multiplied times 1, and for the denominator clearly. We can note that the xcg is equal to 150 millimeter, that is equals to b along xy axis. The reference axis in this case that I used is the blue one, with the x and y in capital case. YCG is equal to 150 millimeter, but is a over 2, this distance here from the point 1 to at half of the web. So the CG is placed just here. but we should see that the CG for this section is also the shear center of this section. So we should see this in between a few minutes, I hope few minutes. So the moments and product of inertia. How I said before, now we must calculate also the Iyy and the product of inertia Ixy. In the previous exercise that I made for instance in the C section, the channel section, that section was one time symmetrical. That in that case the Ixy was equal to 0, but now this section not is symmetrical. So Ix(x1) is the moment of inertia with respect to this axis x, that is the xcg axis if you want, is equal to the moment of inertia, as always, with respect to its own centroidal axis of the first rectangular shape, that is b times t at third power divided 12, plus using the theorem of parallel axis, plus what? A1, that is this area, the area of this rectangular shape, multiply the distance from the G1 to the CG. So yj1 minus ycg is this the vertical distance, if you want, at square power, and this quantity is equal to this quantity here. But I reported also that the moment of inertia I can write as also as a at third power times t divided by 8, because if you make some calculus that I don't report, but I leave to you to prove that Ixx1 after some calculus is equal to a times t at third power divided by 24 plus a at third power times t divided by 8. But the thickness, this is a thin walled section. That means that the thickness is much lower than the other geometrical quantities of our section. T is much lower than A, T is much lower than B. So this quantity here is much lower than this, because this is the T at third power, but this is A at third power, but A is much higher or T. So Ixx1 is can be approximated reasonable at the A at third power times T divided by 8, and you can prove this. You can prove this making this calculus. So Ixx1 is equal to Ixx11. So here is 6.76. Here we have 6.75. But so it's very low, very low quantity in variation. So it's the same things. So the Xx2 is equal to the only the moment of inertia with respect to its own central axis, because this Z2, G2 is equal to CG is located at the same position. This quantity here, if I made YG2 minus YCG, this quantity is equal to 0, so Ixx2 is equal to this quantity. Ixx3 is equal to Ixx1, and because the lower flange is the same of the upper flange, so we obtain that Ixx is equal to 2 times Ixx1 plus Ixx2, and we obtain this quantity here of moment of inertia for the z section with respect to x-axis. Iyy now is calculated as the flipped of the Ixx. Now we must make this calculus here. So the base of the rectangular shape at third power, the base in this case of the first rectangular shape is b, so b at third power times t divided by 12 plus a1 times now the distance from the x coordinate, so xj1 minus xcg at square power, and this calculus is equal to this quantity. Also here, if you make some calculus, you can prove that the IY1 is possible to write also as a at third power times t divided by 24, and you see that we obtain the same thing. IYY2 is equal to t at third power times a divided by 12, but you can see that now IYY3 is equal to IYY1, but you can see that IYY2 is a 2 order of magnitude lower than IYY3 and than IYY1. So if I write IYY as the 2 times IYY1 plus IYY2, is the same thing to write IYY approximated to 2 times IYY1. So you can see the number is the same, because this quantity is 2 order of magnitude lower than this quantity here, IYY3 and IYY1. So we have reached the value of IYY. Now Sy is equal to 1 times 1000 Newton, if you want, because we have Sy that is equal to 1 kilonewton. The product of inertia is equal Ixy1 is equal to the area of the first rectangular shape A1 times, now this is the new thing of the for our exercise, the distance from the first centroid to the centroid of Z section times the yj1, the centroid of along the y direction of first rectangular shape, minus the ycg. So if you make this calculus, we obtain exactly this quantity, and this Ixy2 is equal to 0 because yg2 and ycg is the same thing. So this difference is equal to 0. So clearly all these quantities a multiplication. So 0 multiplied by other quantities that are not 0 is equal clearly to 0 millimeter at 4 power. Ixy3 is equal to Ixy1. So Ixy is equal to 2 times Ixy1 plus Ixy2, that is equal to this quantity here. So this is all the section properties that we must calculate to obtain this. Now I reported the integral directly in the MathCAD. So we see this Q12, that is take this, you can understood what I said, 1 and 2, and S1 is our chosen abscissa in the positive direction for the shear flow. So now the integral is equal to as said before, to Sy times Ixy divided the denominator Ixx times Iyy minus Ixy at square power, multiplying for time by the integral from 0 to S1 of t times S1 minus b. Because I obtained this quantity here, this is an equation for the x coordinate. So this integral here is for the y coordinates. In the previous exercise made on this channel, we have seen all the y coordinate. So the quantity on this integral here. But now we have also an equation for the x coordinates. So we must derive this equation from this calculus. So when x1 is equal to x1 is this point here, but this point here is placed at the negative x coordinate, that is equal clearly minus b. So we have when x1 is equal to minus b, s1 start from point 1 is equal to 0. When x2 is equal to 0, point 2, the coordinate along x of 2 is equal to 0, the s2 is equal to b. So we finally obtain x minus b divided by 0 minus b, but this I can put here b equal to s minus s1, that is 0, s2 minus 1, b minus 0 is b, I put here b. So the equation that we obtain is b times x plus minus times minus same plus b at square power is equal to b times s. So this is equal to solving for x is equal to minus b plus s, and this is the equation that I must put in this integral here. So t times s1 minus b, s1 minus b. So for the y coordinates, so for this integral here, I must take the same logical flow. So I write here, when y1 is equal to the y coordinate of the point 1, what is? Is this coordinate here, this quantity here, and that is placed at minus a over 2, because this is the negative direction for the y. So when y1 is equal to minus a divided by 2, s1 is equal to 0, because we are starting from point 1. When y2 is equal to minus a divided by 2, because point 2 lies on the same line of point 1, so this distance here is the same of the point 1. So when we have this, s2 is equal to clearly to b, because we have arrived to the point 2. So the equation is y minus y1, that is plus a2, because we have a minus sign. So y2 minus y1 is clearly equal to 0. That is equal to s minus s1, that is 0. s2 minus s1 is b minus 0, so b. And we obtain b times y plus b times a divided by 2. 0 times s is equal to 0, so 0. And so we obtain here the equation solving for y, that is equal to minus a divided by 2. And this is the equation that we must put in the integral for the t times y. So if this is the x equation, and we must put in this integral this quantity here, and for y we obtain y is equal to minus a divided by 2. So in integral here, in this y we must put t times a divided by 2 with the minus sign. So if you make this, we obtain this quantity here. So now this is a symbolic calculus of this integral, so we can resolve this clearly manually, that not is difficult for you resolve this simple integral, but with the simplify command of MathCAD we obtain a symbolic resolution of this integral that we can see now. We expand this quantity, so this is this quantity here or this quantity here, but don't take in account how is the equation of this stuff that is very scary, but we now must to know how is the shear flow at S1 equal to 0 millimeter. Clearly, because here So in the left side of point 1 we have no area, the same discussion made on the previous video in the exercise of the channels of the exercise of channel section. On the left side of point 1 we have no area, so the moment of the first moment of area is equal to 0, so clearly the shear flow also equal to 0. And this is why the reason because I choose always the point that on the its left or its right have no area, because I sure that here the shear flow is equal to 0. So clearly at point 1 we must obtain a shear flow that is equal to 0. So this is a good thing for us. Now, but this shear flow is always positive, always negative, as another point that this shear flow is equal to 0? Yes. So we must to investigate where the abscissa S1 is such that the Q12 is equal to 0 again. So with MATCAD we must solve this equation. So for you, when you derive the shear flow as a function of S1, you must put the equation that you obtain in S1 equal to 0. That is clearly, if you see here in a quadratic equation, you resolve this quadratic equation and obtain two roots. The first root is 0, clearly at 0 millimeter we have Q12 is equal to 0. The other roots were that is such that the Q12 is equal to 0 is 99.1 millimeters. So at this distance our shear flow returned to 0. So I made a ratio with respect to B, length of the flange, with respect to the length of the web. So we obtain that this quantity with respect to the length of the flange is 0.66. So is about 60-70% of the length of the B of the flange, and with respect to the length of the web is to approximately to equal to 33% of the length of the web. So now I want to know if this shear flow is always positive or is always negative. Clearly, if at this distance we obtain that the shear flow return to 0, clearly this shear flow starts from a certain value that is negative, this value here, and arrive to another value that is positive, that is this value. So I evaluated this shear flow at S1 zeta 2. This is the method of MATCAD to pick this quantity here. So at this quantity here divided by 2. So for this quantity here minus, I'm saying, we obtain that at S1 of 99.11 millimeters, Q12 evaluated at this S1Z is equal again 0 Newton divided by millimeter. So if I write S1Z divided by 2, obtain clearly a quantity minus of S1Z. So I want to investigate the Q12 at this quantity. S1Z divided by 2 is positive or negative. So in this quantity here is clearly negative. At the location of S1 zeta 99.11 millimeter is clearly 0 Newton over millimeter. At B, Q12 is positive. So we just obtained that for all the S1 measure of the S1 zeta, the shear flow Q12 is positive. For all the S1 of S1 zeta, the Q12 is negative. So you obtain this stuff investigating this shear flow. So Here I reported also the tau, the direct stresses. So now we can switch to calculate the shear flow in the web from point 2 at point 3 as a function of S2. Now we must sum to this shear flow the shear flow that we have obtained, that is this shear flow Q12 at B. So the equation is the same. Now change clearly the equation for x and y. I derive this equation, but for the lower flange I leave to you as exercise to derive the equation for x and y. But you, if you are smarter, and I know that you are smarter, the equation is similar to the upper flange, because the two flanges are equal from this exercise, a same orientation. So S3 from left to right, S1 from left to right. So now I can write the equation for the quantity 2, 3. So when we have at point 2 equation for x2 is equal to the x coordinate is equal to 0 of point 2. X2, when x2 is equal to 0, S2 starting from point 2 is equal to 0. When x3 is equal to point 3 is clearly the same x coordinate, because 2 and 3 lies on the same line. So when x3 is equal to 0, S3 now is equal to the length of the wool web and is equal to A. Here we must change this quantity here. X minus x2 in this case is 0. In the denominator, 0 minus 0 is 0. S minus S2 0, S3 minus S2 is equal to A, and now we can change this quantity here, and we obtain, if multiplying cross direction, we obtain A times X equals to 0 times S0, so X is equal to 0. I must put in this integral here x equal to 0, so we see this quantity. This is the reason because we see this 0 millimeter here, because MathCAD must have the quantity, in this case dimensional. So the first integral is completely absent, so I have no sense this integral. It's such that all the first part of this shear flow is equal to 0. We now survive all this quantity here, where you see the equation for dy, that is S2 minus A divided by 2. I can derive this formula, this equation for you. So we have, when the y2 and y3 now here, S2 and S3 here. So when y2, the coordinate y2 is, clearly the point 2 is located at minus A divided by 2 as y coordinate, minus A divided by 2. S2 start from the 2.2, that so is equal to 0. When y3 is equal to y3 is this quantity here. The point 3 is located at positive A divided by 2. So we have A divided by 2. And S3 is equal to A. Now we obtain y minus time minus sign is plus A divided by 2. A divided by 2 plus A divided by 2 is equal to S0 divided by A minus 0. That's solving, we obtain A y plus A at square power divided by 2. This is A equal to AS. So we solving for y, we obtain minus A divided by 2 plus S. that is the equation that you see here. So S2 minus A divided by 2, S2 minus A divided by 2. So I put now this equation in this integral, and we obtain clearly this quantity here. If you make this calculus, always this is the symbolic calculus, so if you make this calculus is not terrifying like this. But we obtain a similar thing, but not as difficult for you. So Q23 at 0 millimeters is equal to 1.43 Newton over millimeter. Q23 evaluated at A divided by 2 is equal to 4.27, and Q23 evaluated at A is equal to at 1.436 millimeters. So clearly the shear flow returned to the value of Q23 at 0 millimeter, because now we starting with the next shear flow, that is this quantity here at 0.3, but at 0.3 we have the same shear flow at 0.2. Now I want to know where the shear flow is maximum along the web. I must derive this equation with respect to S2 and obtain this quantity here. Solving for S2, I obtain that the maximum shear flow is explicated when the S2 is equal to 149.9999 millimeters. That is clearly equal to A divided by 2. So in correspondence of the CG, we have the maximum shear flow in the web, and we obtain clearly this quantity here. So A2 we obtain, so you see this quantity here is higher than this and then this. So the next shear flow is the shear flow Q3 as a function of S3, that is equal to the sum of the previous shear flow calculated at A, so Q23 at A, plus our shear flow formulation, that is this. If you resolve this integral, obtain stuff like this, all this the number. So now I want to know where this shear flow is again 0, because we seen that for the upper flange we obtain a point where the shear flow return to 0. Clearly also here we obtain this point. So the first point here for 49.55 plus 100.44 millimeters and so on is the end of the lower flange. So if you make this sum, we obtain 150 millimeters. So clearly at end of the lower flange at 0.4, on the right of 0.4 we don't have an area, the shear flow is 0. So this is a good for us, because we obtain a right response. But the other point, this other point here, is where the shear flow return to 0. So I evaluated the shear flow at this distance, the second point, S30 divided by 2, I obtained this value of shear flow. At 0, at the same value, so at the S3 zeta, the shear flow at the value of S3 zeta is equal to 0 Newton over millimeter. So this is the distance clearly where the shear flow return to 0. And now I evaluated also the shear flow at point that is greater than the S3 zeta. So 1.05 times S3 zeta, the shear flow is negative, and at point B the shear flow is 0, because we have 10 at minus 16 power, so is 0.00000, so is equal to 0. So in this case we obtain for the the lower flange, that for the lower flange we obtain that for all the S3 major than S3 zeta, the Q34 is minus than 0. For all the S3 minus of S3 zeta, Q34 is positive. Okay, so we obtain this quantity for upper flange. This is for lower flange. So we obtain this quantity. We have clearly a point that is equal, so this is S3 is equal about of 0.33 of A, where the shear flow at this point, clearly so for S1 0.33A, Q34 is equal to 0, Q12 is equal to 0 at this quantity, at these two value of the abscissa 3 and 1. So the resultant and shear center location, now shear center location from CG. I splitted the integral in two parts, so from 0 to S1 Z and the second resultant from S1 Z to B. So clearly if I sum these two quantities, I obtain R1 to X that is equal to 1.881 Newton. So this is the integral of the shear flow as a function of S1 give us the S1 give us the resultant. The resultant along the web, so R23y in y direction is equal to integral from 0 to A of the shear flow Q23 as a function of S2 is equal clearly at the shear applied on our section, but we see that the shear ratio along y is equal to 0.997. That means that if I clearly also for the lower flange I divided the integral from 0 to S3z from S3z to B, obtain these two quantity, and if I sum these two quantity, obtain the resultant along x for lower flange R3 for x. Now the resultant along x direction, that is the sum of these two quantity R12 R34, is equal to 3.762 Newton. Now if I make the shear ratio along x, Rx divided Sy is equal to 0.004. So what means that? Means that the about of 0.5% of the shear applied on our section is explicated along x direction, and for the 99.7% the shear flow is absorbed along the web. So in the z section we don't obtain the that the Rx is equal to 0. This is a particular thing. If you make shear ratio y plus shear ratio x, approximately is equal to 1. So 100% of the our applied shear load. So in Z section, a small quantity of the shear applied shear load acting along the x-axis. So the Rx is not equal to 0, how seen for the channel section, where in this for this channel section the shear ratio along y is equal to 0.9999, that is equal clearly to Sy. So in other words, along the x-axis the forces are not balanced. So we have a residual force along x-axis, and the force is also, and the part of clearly a great part of the shear load is absorbed from the web, but a small quantity is also absorbed from the flange, and these quantity absorbed from the flange are not balanced because the Rx, the resultant along x direction, is not equal to 0. Now if we move to calculate the shear center with respect to the CG, we obtain Ex, that is the distance clearly this is the the diagram of the shear flow, where when the arrows move from right to left for upper flange, the shear flow is negative, and vice versa for the other arrows. Now, on the right side, we obtain the shear flow diagram. So we obtain a negative shear flow, positive, here is all positive along the web, return to positive here with the same value here, this value is the same that we obtain here, and the shear flow return to a negative value and at 0.4 with 0 Newton over millimeter. This is a qualitative draw of the shear flow of the zeta section. Now, I want to show you how to calculate the AX, that is this quantity. We must apply an equilibrium at moments. So, we obtain that R12X generate a moment, a torque with respect to the z-axis that is orthogonal to x and y. So this case is directed through you. So in exit from the screen, we obtain R2x generate this torque here that is clockwise, and this for us is a negative torque. But first of all, Sy generate these moments here that is counterclockwise, so positive for us, is Sy times E must be equal to R3-4x generate a same moment, so directed in same direction, and this positive, and this is equal to R3-4x times A divided by 2. A divided by 2 is the arm of this resultant, minus R12x times A divided by 2. E is equal to R3-4x A divided by 2. I can group this quantity and I can write A divided by 2 times R3-4x minus R12x divided all by Sy, that is the shear load applied. This quantity is 0 millimeter because R3-4x and R12x is equal. So the two resultants is equal here. So if you see my cursor, this is two quantity is equal. So we obtain 2.6 times 10 at minus 15 power. So is 0.0000 and then 2665. But is clearly x is equal to 0, and clearly ay is also equal to 0 because in y direction the shear load is this. As y, if I this shear load have no harm with respect the x axis, and so clearly we obtain that 0 is equal to 0. So Ey is equal to 0 millimeter, and here we obtain the diagram of the shear flow, but in as a single function Q12, Q23, and Q34, and we see that this is here negative, at this point is 0, and return positive. We have a parabolic shape trend along the flange, this is S2, and in the lower flange the shear flow through to the positive value at a negative value here, and return to 0 at 150 millimeters, that is the length of the flange. So this is all for the zeta section, and this is all for the open section, thin walled open section. I made two exercises, channel section, and these I can hope that are clear, but in the future I can make other exercise, but for the next video I switch on the closed up section with directly an exercise. We will see a tube section, and we calculate the shear flow for a closed thin walled section. So the video is ended here, and we will see at next video. Bye.